Make sure we're all good. Okay. Got the thumbs up, so we're going to get started. And of course, first, before we get into it, I'd like to start with some thank yous. Of course, thank you to Intelitech for the venue and the food. And thank you all for coming. I'm amazed people actually showed up to a mundane intro to machine learning. Maybe if I called it an exciting intro, we might have had more. But we'll take that to start with. So let's get into it. I'm going to start with establishing our goals for tonight. If there are 2 questions we can answer, I'll be happy. First, what is machine learning? And the second one, how does it work? Hopefully without getting into too scary of math, but we'll see. I might get a little carried away. But before we dive into it, I should probably introduce myself, tell you who I am, and without getting too philosophical on the question, my name is Clayton Gravatt. I have a Bachelor's of Science in Data Analytics, which is a fairly broad spectrum data-ish degree. And so I don't mean to misrepresent myself as an expert in machine learning. I do have some academic experience in it, but I am by no means specialized in it. Previously, I have had an internship where I got to work with predictive analytics in the financial tech industry. We were using machine learning to help predict who's going to repay their loans, and we found some degree of success. And currently, I am a data analyst here at Intelitech. Most of the work I do revolves around business intelligence, particularly moving data around, modeling that data, and then visualizing that data, and hopefully soon more of predicting that data. So without further ado, let's get into our presentation. And to start with, I'd like to start by defining what artificial intelligence is. Looking around the web, there's a lot of existing definitions, but they all follow a similar pattern. They all try to define it as intelligence demonstrated by computers, or artificial intelligence is computer intelligence, which is right, but it's not very helpful, because in the phrase artificial intelligence, computer intelligence, the artificial part is not that difficult to define. It's the intelligence part that's more interesting. And so to that end, I offer my own definition. While it's not perfect, it's useful for me. Artificial intelligence is as simple as computers making decisions based on their environment. And to illustrate that with a simple example, hopefully everyone has played Pac-Man, or at least knows the premise. You're the little Pac-Man running away from the ghosts that are trying to catch you. And while it's not super amazing or complicated, it does still meet my criteria for being AI. The ghosts within it do react to their environment and make different decisions. They have to know which path they can take, and at any step, they will react to differences. So if Pac-Man goes and picks up the power pellet, they change their behavior, they react differently. So they'll run away from Pac-Man instead of chasing towards him. So neat, but not that interesting. And you might be able to easily enough imagine how someone went about implementing this. Like the ghost behavior is not that complicated. You can think, okay, at each step, figure out which directions it could go in, and of those, which one brings me closest to Pac-Man, and go that way. So not too complicated. But there are some more complex examples of AI as well that follow a similar grain. Something like autonomous vehicles, speech recognition, object detection, navigation. These are all really cool and really powerful, and definitely AI. But as artificial intelligence gets more complex, it's harder to imagine how you'd go about implementing this. It's harder to think of a step-by-step program you could write out that could detect objects. And that's where machine learning comes in. And machine learning is just a type of artificial intelligence that allows computers to learn without being explicitly programmed. And now I have a funny looking E symbol here. The machine learning E thing is AI. Does anyone in the audience happen to know what that symbol means? Joseph, would you like to venture a guess?
Contains.
Contains, yep, close enough. Machine learning is an element of artificial intelligence. That's all that symbol means. And while people that know math symbols, that might be obvious to, it's a common barrier to entry to data science, that they obscure these pretty simple concepts behind these somewhat obtuse symbols. And that's something that I'm going to try to combat with more visualization-based learning. And to that end, I have a diagram on the side that shows a circle of artificial intelligence, and within that, machine learning. So within the big realm of artificial intelligence, machine learning is a part. And that's just like saying that not all bugs are insects, but all insects are bugs. It's a subset of. So hopefully that makes it a little easier to understand. And within machine learning, there are a bunch of divisions. Today, we're only going to talk about a small part. We're only going to be looking at supervised machine learning. But just to give you a general overview, supervised machine learning is a type of machine learning where you have historical data that's already labeled. we already have some examples of dog and cat pictures. We're just going to teach a computer to recognize those and apply that learning to new examples in the future, to future predictions. Then you have unsupervised learning, where we don't know the answer already, we don't know what the pictures are, or we don't know what's in the data. We're just hoping that the machine learning algorithms can help us find something and help us find patterns within it, but we don't know what we're going to see. Then you have reinforcement learning, where you're just trying to maximize some goal. This would be like seeing how far you can get in the game Flappy Bird or Pac-Man, how high of a score you can get, but there's not a defined answer you get at the other end. And then you have sets of ensemble methods, which are just smart ways of combining multiple models together to get a better answer. And then finally, you have something called deep learning, which is similar to the other kinds. It just uses really big and complicated models that are loosely based on the architecture of the human brain, but same basic idea. And before we go any further, I'd like to revisit my earlier definition of machine learning and pinpoint what I mean by explicit programming, where machine learning doesn't require it. So explicit programming and explicit instructions are step-by-step. You can think of it like making a recipe to bake a cake, for example. Someone can write out the exact instructions on how to bake a cake, and anyone that can read and has some knowledge of how to cook can follow those exact same instructions and get the cake out at the other end. And while useful in most situations, it does have its shortcomings in that it requires the programmer or the chef or the author of that recipe to know in advance how to do it. And that does have its shortcomings because some problems are hard. Some problems are harder to solve. And an example of that would be, how would you tell a computer to differentiate between pictures of a dog and a cat? I'll give you a second to think about that because it's not, it seems easy, and like a 5-year-old could do it to a reasonable degree of success, hopefully, but how would you go about telling a computer to do that? Well, maybe you can start looking at some patterns. Maybe the cat has a more triangular nose than the dog, but how does a computer know what a nose is, right? And this is where machine learning comes in, and we're going to try to solve a problem. But picture recognition is a little hard, so we'll start with an easier problem, but I'll set the stage on one. Housing value. So I have a problem. I have a house, and I would like to know how much I should sell that house for. And it's difficult because I can't just look at a price tag on the outside of the house, even though in the picture it looks like there's a nice price tag on it. It's not obvious to me what the price is. But there are attributes of my house that I could measure. I can measure the size of it, how old it is, the color of it. And my hypothesis is that I could use these features or these attributes of my house to predict what its price would be based on historical data. And of course, being the astute, data-driven person that I am, I've definitely collected some real historical data of actual houses that I definitely didn't just make up for this example. And I've collected historical examples of the size of a house and the price that it sold for. And I've plotted those examples here. On the x-axis or on the bottom, we can see the square footage or the size of the house, and on the y-axis, the price. And each dot represents a different house. And we can see a pattern starts to emerge that as houses get bigger, they seem to get more expensive. So it seems like there's something in the data that I could use. But the problem is this is a Python meetup and this is an Excel graph, so let's transition over. But before we can really get into it, I'll introduce some of the libraries we're going to use. And the first one is Pandas, which is really the data analysis library to start with in Python. And I can't fully do it justice, but the one piece that I have time to focus on for tonight is the primary data structure that it adds, which is the data frame, which you can think of as an in-memory table that has labeled axes. And it's really cool, and it does a lot. But for our intents and purposes here, it's basically just a table. And so here's our first snippet of Python code. I'm going to import pandas in as PD, which is just common shorthand. It's ubiquitous. You can't get away from it. Everyone in every guide always shortens pandas to PD, so I am too. And what I'm doing here is I am reading my Excel file from earlier that I've saved as a CSV file into pandas, or into Python using pandas, reading it into a data frame. So I'm creating my table using the pd.readCSV method. And I am changing it. I'm changing the name of some of the columns to be a little easier for me to use. So instead of calling it size, parentheses, square feet, I'm going to rename that to just size, and price, I'm going to get rid of the $sign, just so it's a little easier for us to use. And I can print it out, and you can see at the bottom that I have taken my table, and now I have it in Python. Now I have my data in Python. We can start doing stuff with it. And if you remember from earlier, I complained about symbols and looking at numbers. Now that's hard. So instead, we're going to try and use more graphs and pictures, which is a much better way of conveying data and conveying information. And to do so, we're going to be using a library called matplotlib, which is extremely powerful, and you can do pretty much anything in it. but it's a little unintuitive and sometimes hard to use. And so I'm not getting too much into it, but just know that it's there and you can use it, and it's okay. So our first graph, I'm not going to get too into the code for it, but basically you can see that it's the same as the earlier Excel graph. I have taken my table or my data frame of size and price values and I plotted it out so we can see there's that same pattern again. Okay, we have it in Python. Now, I told you we're going to use machine learning, and within machine learning, our goal is to create a model to help us predict things. But first, we have to know what a model is, and I like to think of it as just a structural representation of the relationship between variables, which is a little wordy, but basically, it's just the result of fitting some algorithm to an existing data set, and often it's just a function you get out. Hopefully, some people remember back in elementary school or whenever it is, and maybe this is more relevant to some members of the audience than others, but there's something called a function machine that takes some input into a box, does some transformation to it, and spits back an output. And that's basically what a lot of models do. They take some input, they do some transformation on it, some black box unknown transform, and they spit back a prediction or a result. And as a review of functions, they just take some input and map it to some output after some transformation. But the takeaway from this slide is that you can represent a function with a graph, right? So on the left, I have some x values that I've plugged into my function, and I got some y values on the result, and I can plot those, and the result is just a line. So I can represent my function with a line, much easier to see what's going on. Okay, so that brings us back to our goal. With creating this model, really all we have to do is find the function that best fits our data, or find the line that best fits through our data points. And of course, I'm not going to be doing this in a very efficient way. There are other ways to solve that use a little more math. There's a general statistics way using ordinary least squares, bunch of math and numbers. There's a really cool linear algebra way using the inverse of transposed matrices multiplied together, and it spits out this perfect output in one step. Really cool, but we're looking for a more general solution, and we're not requiring a closed form formula to already solve it. We're just looking for a general approach we can take to machine learning. So back to Python, we're going to start by creating a model, and our model is pretty simple. It just has one parameter to it, a slope, and one method attached to it, a prediction method. Of course, our models are useful because they can make predictions. And so that's all I'm making here, a very simple model that just has our slope parameter. And the interpretation of this is it will take some input. In this case, I only have one variable that I'm looking at to start with, size, the size of the house. So it takes my input size, and I can pass it into the predict method of my model, and it will spit back its predicted output. And in this case, our output we're looking for is price. So here I'm adding a column to my housing data frame from earlier. This is the result of passing in my size column, and I spit back out a predicted price column. Now, 100 for our slope is just a random number I've started with. I just have to put something there. I know it's not right, but it gets us going. And you can see that it can make predictions, but just looking at a table of numbers, it's a little hard to see if the predictions are good or not. I expect they won't be because it's just a random starting point, but to better see that, I've added a graph, of course, where in the blue dots, I've added the actual price of the houses, and then in the red dots, I've added the price that I predicted for those houses. And you can see that it's wrong, and you can see that it's off a little bit. How off? Well, about this off, right? Approximately, but while that's easy enough for us to see looking at a picture, that doesn't mean much for the computer. So we need a more objective way of measuring how good our model is. And to do that, use a little math, hopefully not too bad. We're going to use something called R squared, which is called the coefficient of determination. And basically, it's just a measure of how much of the variance we're able to capture with our model, or how much of the relationship our model actually represents. And to do so, we're going to figure out what the sum of squares is, and that is just calculating what the distance is between the actual value of the house and the value that we predicted, finding what that distance is, and then squaring it to make sure that negative values don't cancel out positive values. So we square it so that we don't accidentally pretend our model is better than it is, and we'll divide that by the total variance of the model and then subtract it from 1. Don't worry too much about the steps involved in that, but the output is we have a measurement where a score of 1 would be a perfect model that captures 100% of the variance, and our predictions would perfectly align with what the actual values were. And a score of 0 would be the same as just guessing the mean, kind of like just guessing C on every answer on a multiple choice test. Not very good. So we have a way of measuring our model. Let's see how our predictions are for our starting model that just had the arbitrary slope of 100. And to do so, I'm going to add a scoring method to my model from earlier. And don't worry too much about what it is. It's just the math on the previous page, done it in Python here. And if I put in our predictions that we made with our current model that has a slope of 100, it spits back a score for us of negative 1.16. So worse than 0. We have a very bad model, not very good. But the cool thing is now that we have a way of objectively measuring how good our model is, we could start comparing models. So if I were to make two other models that have random slopes, where the first slope is 150, and the second model has a slope of 75, I can figure out what the scores of each of those models are and compare them against each other. And here we see that model 1 has a score of 0.44, whereas model 2 had a score of negative 2.36. And because model 1 has a higher score, we know that it's better at making predictions and that its slope of 150 is closer to our actual relationship than the 75 would be. So now that we have a way of comparing models against each other, we can start training a model. And this is where the inefficiency comes into play. The algorithm that I've decided to go with is flipping a coin. So the general flow through this code is I'm going to start at my random spot, whatever that is, 100. And I'm going to make a model there and figure out what its score would be, figure out the predictions and compare them and figure out all the errors, get a score for this model. And then I'm going to make another model that's slightly different. I'm going to take the slope of my first model and then flip a coin. And if it's positive, I'll add something to it. If it's negative, I'll subtract something to it. So I'll make a new model that's randomly slightly different. And I'll calculate the score for that new model. And if it's better, I'll change my model to use that new model's slope. And if not, I'll just ignore it and try again. And I will loop through this a bunch of times. So we have a bunch of opportunities to make guesses that get better and better. The number I put in here is 100, but you can start with whatever. And to visualize that, I've added an animation of our line, which represents our function, slowly getting better and fitting through the data. And you can see it. I have a generations counter at the top, which is just a number of iterations that it goes through. And somewhere about 95, it stops, and it actually fits through our data, which is cool, right? Because this is not a very intelligent design. I'm actually just randomly guessing. But because I'm iteratively getting better because of those guesses, our model actually improves over time. And at the end, I get a fit model, a model that is fit to my data and that I can actually start using to make predictions. And so let's do that. Let's say my house, oh, we have a question?
We got a question from the chat.
Yeah, go ahead.
Grant asks, how do you protect from falling into a local minimum?
That is a question that I will come back to later, Grant. Okay, thank you. The question from Grant, someone at Intelitech, was how do you protect from falling into a local minima? And that is not something that I'm ready to answer yet, but I will come back to later when I start talking about gradients. If you see triangles, remind me to get back to that. And another question? Okay, that's a good question. And to repeat that back, the general question was, is it right to use a set number of iterations to loop through something, or would it be better to just have like a while loop that just keeps guessing until it meets a certain threshold or a certain condition? And the answer is kind of. Because we don't know how good the model could get, it's better, or it'd be hard to define an exact threshold, like in an error term. We can't say keep going until the error is 0 because we don't know how low the error is going to get. We don't know how good of a model we can get, but there is some kind of a threshold criteria we could set. We could see if in the last 3 movements we've not gone anywhere, or the last 10 movements, let's say, we could have some kind of convergence detector that detects when the model is done and when the model stopped, and we could exit at that point, or when we reach the maximum number of iterations. Otherwise, we might get stuck in an infinite loop. But you're right, it'd be a lot better to have multiple ways of exiting and knowing that we're done training. Good question. Okay. There's no more questions there. I'm going to move on to my predictions. So my hypothetical house that I definitely have has a has a size of 1,500 square feet. And I can plug that house size into my fit model and make a prediction, and it spits back that I should sell my house for $300,316. There we go. Numbers are a little hard, sorry. And this is cool. Now I have some educated guess of what I should sell my house for. And I don't know anything about property assessment, and I've not done any math that's too fancy. I've just iteratively guessed until I've made a decent model, or as good of a model as I could get here, and I can use this. I can make a Zillow2.com and maybe sell this idea, or maybe not. But our model, of course, does have its shortcomings. We are only capturing one variable so far, only the size, right? So we're not able to answer questions like, what if pink houses are worth more than green ones? Or what if older houses would be worth less for the same size? And along that note, our style of training is very inefficient. We only have one variable, which means when we're training our model, we only have two options. We can either move our one slope up or move our one slope down. So we're going to guess correctly about half the time, or one out of two of them will bring us closer to the correct answer. But if we had two variables, suddenly we have four options. At each step, we can move them both down, move one down, one up. We can move them both up, or one up and one down, which means we'd only guess correctly about 1/4 the time, or we're wasting about 3/4 of our operations. And if we look at a modern example of a machine learning model, modern models usually have a lot more variables. And in the case of OpenAI's GPT-3, it has 175 billion parameters, or variables, that it has to adjust to train. Now, if it only had 175 variables, the number of options would be 53 digits long. And that's only with 175 variables. 175 billion variables would have options would be 53 billion digits long, which that number alone would take me about 520 years just to type out. So either some old guy at OpenAI started a really long time ago, or there's a better way of training models. And luckily for us, there is. And this is where the gradient comes in. This is the triangle, but I'll get to those questions in a minute. And this, I've added this for people that like math. If this means nothing to you, that's okay. I'm going to go into what this symbol means, but it's all good if this is just Greek, because it kind of is. So gradient is an operator, which means that you can apply it to a function, and it changes that function and gives you something else out. And it's an operator that you can apply to a scalar-valued multivariable function. And it results in a vector-valued function. So it transforms my scalar-valued function into a vector-valued function. And each of those elements in that vector, the resulting vector, are the partial derivative of the original function with respect to a different one of its variables. And for those that don't know what a partial derivative is, but do know what a full derivative is, if you've taken Calculus 1, it's like a full derivative, except we treat most of the other variables as constants for that one term. But again, it's okay if that doesn't mean something, just looking at the math. We have pictures too, and basically the gradient is magic. What the end result is of calculating the gradient at a certain point is it results in a vector that points in the direction of steepest ascent. And what that means basically is if I calculate the gradient at some point on a hill, it will result in a line that points uphill in the steepest direction. And this works in however many dimensions. If I just have my little two-dimensional thing, you can see the arrows pointing up the hill. And you can see in my beautiful drawing that I've added, if I have a 3D hill as well and I calculate the gradient at some point, it'll tell me an arrow that points uphill, which is really cool. But how do we use it? What function could we apply this to? Well, if you remember from earlier, we had our r² function, but that's a little more expensive than what we need. We really don't need to normalize it and figure out what the total variance is. All that we really need to know at each step is how wrong our current model is, or the sum of the error terms. And as a reminder, that's just the distance between the prediction and the actual value squared. So what we can do is we can add those all up, and that'll tell us the total error at a given point. And just so you can see what an error function would look like, if you remember, I squared it, and so it results in this cool looking parabola. But the cool takeaway here is that if you see our model being trained on the right, as our model gets closer to the correct answer, as our line gets closer to perfectly fitting through the data, our error function hits the bottom of a curve. That is our optimal solution then is when our error function is minimized, which makes sense because a model that has the least amount of error, that's the least wrong, is the most right. So now we know that if we can find the bottom of our error function, that'll be our optimal model. And so this is where gradient descent comes in. And if you remember from earlier, the gradient and find the bottom of our error function, that'll be our optimal model. And so this is where gradient descent comes in. And if you remember from earlier, the gradient is an arrow that points uphill. And so what I can do is on my error function, if I start at some random point and I calculate the gradient, it'll tell me that the steepest direction uphill is to some direction. In this case, it's to the right. And if I know that the steepest uphill is to the right, that means the steepest downhill would be to the left. So if I just subtract the gradient at any given point, it will move me closer towards the right answer, or at least towards a righter answer. And earlier there was a question of how do you stop it from getting caught in a local minima? And I believe that was Grant that asked that question. And the answer is there are a lot of ways. Some of the cooler solutions use something called an exponential moving average of the gradient. So rather than just figuring out what the gradient is at this step, rather than just figuring out the current arrow, what they'll do is they'll instead simulate having a ball roll downhill with some kind of momentum. And so while the ball is rolling down and down the hill, it'll get faster and faster. And so if there's a little uphill, it has enough momentum to go all the way up to the top of the hill and bounce back down the other side, ideally. So there are more clever solutions, and so we don't always get stuck in our local optima, but it is a hard problem. And of course, our error function isn't limited to just be 2D. If you remember, it's a multivariable scalar function we can apply it to. So here we have a three-dimensional graph, but it could be 4 or however many. It's just a little harder to show that visually. But I'm just showing here that gradient descent would work in a 3D space as well. We can just start on a hill and work our way down towards our best answer. So I'm sure you're all excited to see how would I go about implementing gradient descent with Python? Well, personally, I wouldn't. I would just import the solution. This is a problem that's been solved a lot of times, and while it's really important to know how the algorithms work, the mathematical implementation is already out there. And so your job as a data scientist or someone trying to apply machine learning models, you're probably not going to be writing your own model. The challenge instead is just knowing how to apply what's already out there with some tweaks. And that's not as easy as it sounds, because just within sklearn or scikit-learn, which is just one library, it's a pretty big library, but it's just one. These are the linear models that it has. These are just different ways of fitting a straight line through space. And within the big realm of machine learning, all we've talked about tonight is linear regression. And some of these other linear models can be solved using something called ridge and lasso regression, which is just another way of solving a linear model. So there's a lot to it. And it's not too bad, though. Just to show you what that implementation might look like. I'm not going to walk you through all the code, but this is about how big it is. This is just importing sklearn's model and training it on my housing data and then spitting back some prediction. So wouldn't worry about too much of what it is, and it can, of course, be expanded out to multiple variables too. If I wanted to use the size of a house and the age of a house, it's a similar idea. I'd just plug it in to my model and let it train and then use it and get predictions out at the other end. So that brings me to the end of my slides. And of course, thank you all. Thank you all. You've been great. Are there any questions? Reese. Sure. Okay. So the question was, I had some unclear language when I said you put the data in and you let it train. Does it have some program that it executes on the other end? And kind of. What I mean by that is we just have to call a fit method on the model, and then it has its own way of solving it afterwards. So it either has some set of convergence criteria or a certain number of iterations that it goes through, and it has its algorithm for solving our problem for us. And of course, there are ways we can alter that too. And I don't have a good example of it here, but we could train a model using different hyperparameters, which is something we use to tune the model itself. or tune the training of the model, let's say. So a good example would be the number of iterations. I had an iterations parameter earlier that was the number of tries it's allowed to have before it has to stop, and I could change that. That'd be a hyperparameter because it pertains to the model itself rather than a representation of the data. Does that answer your question at all? Good. Okay, I got a thumbs up. We'll take that. Any other questions? Back to my question slide. Anything from teams?
Can you go back to almost the beginning? Can you differentiate between those three?
Things that fit into each category of deep learning. Sure. Let me see if I can find that. This one? No, this one.
Yeah.
Okay, so.
You've got some stuff on the right there. Can you just give us some information?
Oh, sure. So the stuff on the right, so there's two pictures. One is just kind of a Venn diagram, not really. Artificial intelligence as a whole is just any program that can sense, reason, act, and adapt what I would say is something that can react to its environment. This could be something as simple as a Pac-Man ghost, something that's able to make a decision on its own. And then within that realm, you have machine learning, which is basically just a way of training these AI, these artificial intelligence things, these artificial intelligence programs.
The training piece here, the difference here is rather than me having a statement that says, if Pac-Man is this far from this location, do this, they're going to have a whole bunch of data. Is that what that means?
Right. And to repeat that question back to you, whereas general artificial intelligence could just be a series of if statements that says, if Pac-Man ghost is here and Pac-Man is somewhere else, do this thing. Whereas machine learning is based on a bunch of data. Yes, rather than having to explicitly write out, do this step, then do this step, then do this step. Instead, we have a bunch of historical data that shows whatever relationship we're trying to capture. And then we have the computer look at that data and figure out how to make an AI out of that, I guess. So you could think of machine learning as a way of making AI without having to explicitly write out everything the AI has to do. Instead, it's a way of letting the AI figure out how to get better on its own.
So we're at a point now where, for many scenarios, I don't have to know math. These are all algorithms that already figured out. I mean, I may need to know basic math, but I probably don't need to know derivatives or partial derivatives or anything like that. Because essentially, I can tell the program, here's the data, run, build a model, and then give me a curve, for example.
Yes, kind of. Do you need to?
Where am I listening?
Okay, so you need to know math in the edge cases, I would say. So while anyone could take an existing algorithm, so like sklearn's SGD regressor, just some existing thing, and apply it to their set of data, they can get a model out of it. But it's not necessarily the best model that's possible. There is still a lot of room for interpretation, I'd say, and this is where feature engineering comes in, whereas just a generic person first approaching this problem may have some idea of the features or the variables that the model should be looking at. A lot of the applied machine learning comes in when you're deciding what variables to feed in and how you could transform those variables. So when you know the math that goes behind some of these variables, you'll know how to change things, or at least have a better idea of how to change things to make a better model. An example of that would be something more simple like linear regression, fitting a straight line through data. Well, what if my data points aren't in a straight line? What if they're in a parabola, a parabolic shape? Well, if you know a little bit of math, you know that you could take the square root of x squared to get x back. And that transforms my parabola to be more linear. And so I can apply math to it to get a better answer.
So my question is, do I need to know that, or can I just say, well, we'll figure out which approach to use? Because eventually the complexity is going to be beyond what I can see, and the computer surely can figure out that I should use a parameter way faster than I could to say I need to do sine wave or something else.
Okay.
Making sense?
That is making sense. And in a lot of situations, that can be the case, but the more complex the problem is that you have to solve, the more data you have to have. So a lot of the problems with machine learning nowadays is not so much a math problem, it's more of a data problem. But if you don't have enough data to accurately train your model, to just let it figure it all out on its own, then you may need to help it along. And in order to know how to help the model, you have to know how the model works. And so you might have to know some math to help it along. But you're totally right that the existing machine learning models can do a lot. And I briefly glanced over, let's say, deep learning. And I said it uses big and complex models. And a good way of thinking about deep learning would be it's like a Build-A-Bear workshop for making machine learning models. Instead of just having, the model that I apply, you have to build your own model using Lego pieces, let's say, building layers to your machine learning network and knowing how to fix certain problems that arise from that would require knowing a bit of math. There's a problem that you can run into in wide neural networks called a vanishing gradient problem, where when you have a bunch of layers and you're trying to figure out the gradient at a certain step, well, you lose a little bit of information as you go back and your gradient will flatten out. And so by the time you get to an earlier layer in the model, without knowing what layers are, it's like a bunch of models that talk to each other. By the time you get back to one of your earlier layers, you don't have enough information to really compute an accurate gradient. And you wouldn't really know how to solve that without knowing what the gradient is in the first place. And the way you do solve that is by using a different activation function within your nodes, within your neural network. But in order to know to do that, you have to know the behavior of those functions. And while I guess you could know that the ReLU, rectified linear unit, performs better in cases where you have a vanishing gradient problem, just knowing that, like just knowing those words, I guess that could help you, but it'd be a lot better to know what the gradient is, what a rectified linear unit is, and how applying that could help you. It adds some non-linearity to the model, but it's still similar to a line, and it helps you solve your problem. And alternatively, you can have the exploding gradient problem. There's also all sorts of problems that come up, I would say. While I may paint the picture that machine learning is easy enough, you just throw some data at a model, there is some more nuance to it.
I'm in no way trying to simplify it. I'm trying to understand how advanced technology is. For example, the very step of deciding which algorithm to use could be a machine learning problem. And it could go ahead and run through some algorithms to try to figure out how to narrow down which algorithm I should be using that just apply that on itself. It should be able to narrow down which algorithm I'm trying to solve the machine learning problem, in which case eventually there's a problem. It's just a machine learning problem which is solved itself.
Ideally. So
a long ways from that. I mean, I'm not trying to be facetious.
Okay, so let's see if I can summarize. The gist of the question was that, okay, the problems of machine learning sound like they can be solved by adding more machine learning models to it. Models that can solve how to make more models, and it's a vicious cycle that gets bigger and bigger with a domino effect that eventually you don't need people. And then the machine learning model knows how to train the next model, which knows how to train the next one, and there doesn't need to be any user input. And to some extent, that's true. In some cases, you can apply optimization machine learning models, such as, I think I see it, a genetic algorithm under reinforcement learning, which during an internship before this is one of the approaches that I took to figuring out which model I should use. Reinforcement learning based optimization model that you put on top of another algorithm that picks which model I should apply to my actual problem. And so yes, there are other layers you can add onto it. But to get to the question of where we are now, I don't think we're there yet. There's some existing offerings like AutoML from Azure, where it tries a bunch of different models and tries to figure out what the best one is. It applies something called automatic featureization, where rather than having to extract the features from my data, do some cool transforms, maybe take the square root, maybe fill in the blanks with some means or something, it will figure out what it thinks a best approach would be. But the complexity, I think, is probably still holding us back. I think an example might be when you're trying to train a deep learning neural network, it could take hours to solve one, let's say. And so the premise of using some other machine learning algorithm to solve them requires having a bunch of data, right? Machine learning algorithms require data to do it. And so the time it would take to generate enough of the lower layer machine learning models for the higher layer one to have enough data to train itself is still probably outside of the scope of what's applicable and useful.
How do you know when a problem?
And I'm not an expert. Like this is what I've read. So
we had from online was from a few minutes before Mark's questions was, what about things like images, such as complex data sets?
okay, what about things like images such as complex data sets? That's a good question. And the answer to that, which I think I'm answering your question, is how computers can look at images is you represent that image with numbers and math. So within an image, all an image is a bunch of pixels. And each of those pixels can be represented by numbers, like RGB or whatever it is. You could have numbers that represent each pixel. And you can take that big array or big table, let's say, of numbers, and you can transform that into a set of features. And there's other steps you'd apply to it. You might apply some a convolutional filter to it or some other edge finding algorithm that prepares the data first. So rather than having just a raw input of the pixels themselves, maybe you calculate how different is this pixel from the pixels around it. And then you take that smaller description of each of those pixels and use that as your features, your set of features that you plug in to your machine learning model to train. And then you can take any future pictures that you want to classify, perform that same transformation to them to get a vector or an array or a set of numbers, and make your prediction off of that. Hopefully that answers your question, unknown person in the audience.
It seems like there always has to be a fitness function that needs to contain value judgment.
Seems like there always needs to be a fitness function that contains value judgment. If I understand your question, yes, you have to have some way of assessing how good a model is at any given point, so you're able to know if a change you made actually made it better. There has to be some way of knowing how good a model is. And that goes into interpretation of models as well, which is another problem for the data scientist or the person behind the machine learning model, is that you can't just trust the model, right? It's this good or 5 good. What does that mean? And actually interpreting what all the associated scores are, there's not just R squared, there's a whole plethora of them, and each one is more suited to different tasks. Like in classification, you might be looking at the accuracy as well as subsets of that, so like the precision and recall, and I'm not going to get into what all of them are, but there are a lot of them, and knowing what each one means and being able to convey that requires some knowledge of math, I guess. So hopefully answering a couple questions at once. Reese.
Yeah. List of languages, is like Python on the top one. Is there a way to count out, like, if you were going to go create something, would you use Python, or is there another language you would start with?
Okay, this is a fantastic question. What's that? Okay. Our resident Python guru is not allowed to answer this question. Okay, so the question was, is Python the language for machine learning? How do you decide which language to use? Are there others that would also be better suited for it or equally suited? And I'd say the top competitor for Python would be R, which is more of a statistics-focused language, and it can make pretty good machine learning models as well. But I think because Python is a more general-purpose machine learning language, it has a wider acceptance, and there are a lot more people that use Python, and so there's a lot more built within Python. And so while I could make an equally good model in the language of R, if I wanted to use that model and I wanted to put it somewhere, Python would be generally a better choice because of existing things like the SDK for Azure, or the software development kit for Azure. So when I go to deploy the model, Python, I can deploy it using Python. I can use Python for my web thing, hosting Python. If I want to do anything else along with that model, I can build it all in Python. And so I think Python's probably the best answer. And it's not just because I only know how to program in Python, but it is.
You shouldn't answer the question either.
Maybe not, but it sounded all right.
How do you know when a problem is? How do you stop? How do you know when to stop the problem? So is it just the same hyperbola graph, you just figure out, yeah, this is nothing.
How do I know when to stop because a problem doesn't seem solvable? When the people paying me to solve the problem have decided that that's far enough.
The compute expense is too high, we spend enough of the budget.
Right. It is kind of hard to tell, I would say. There is, I'd say that a way of measuring how good a model is, you can calculate the score for it, and that the amount of effort that you put in to training your model is not always the equivalent reward you get at the other end. There's a lot of setup to it, and then you'll make a big breakthrough. You'll find some new feature to add to it that's great, and then you'll kind of flatten out for a while. And I think that a problem is solved when your machine learning model is good enough. And so it's inherently subjective. Depending on your application, you might need something better. So if you're like screening for cancer or something and you're trying to detect cancer in images, that's probably a little more important, and you'd probably want to put a little more effort into it, and you'd want to eke out that little bit of performance at the end. Like there, a difference between a score of 98% and 99 is probably pretty important. But on something else where, I don't know, I want to fit a line through data, it's just an academic exercise, maybe a score of 0.94 is good enough.
So the opposite, I don't know where to stop. In other words, the cancer problem is a great one, but I haven't made significant progress, and my compute expense is huge. How do I figure out if I should just not get narrow in this problem, I should stop?
Well, if you already know that you're not going to narrow in the
No,
problem, you
the
should stop.
question,
Oh, how do you know?
How do I know that I should not continue?
How do you know that you
Just finance.
How do you know that you shouldn't continue? Yeah, probably. I'd say that's more of an economic question, because in the real world, of course, things have costs and things have benefit. People probably aren't just making machine learning models just for the fun of it. And if they are, then when they're not having fun, that's a good place to stop. But in a business setting, then when the application that you're trying to build this machine learning model for is good enough, and I mean that really, like, when it's able to make accurate enough predictions that are good enough for you, maybe that's a good place to stop. And maybe an example of that is, I think Elon Musk described it as the trailing nines problem, when his cars, the self-driving cars, do they have to be 99.9% better than people? Do they have to be 99.99%? How many nines do you need? And I think you can really only evaluate that in context. I don't think there's a general golden rule, this is when you stop. Maybe when it has 100% accuracy, maybe that's a good place to stop. But when you're not making progress on a machine learning model, then, I don't know.
I think it makes sense of way to know when to stop when you actually got the solution. Still not got anything, that's when it's hard to figure out.
Right, then it is
I
hard.
figure out when to stop on a problem that you're actually working towards solving. If you haven't figured out what to do, it's bad thing to really do.
That is, and something important to keep in mind there is that inherent to all machine learning models, there is a certain degree of bias. We are simplifying relationships. We are not, like in our example model, we're not actually measuring each tile of the house, each germ on the wall. There's a certain amount of simplification that goes into making a machine learning model. And when you understand that, you know that all models are wrong, but some are useful, right? Like no matter what, your model is probably not going to be perfect, but it could be useful. As long as it's helpful, it's a good model. Unless it's not helpful, then it's not a good model. Anything else? Okay, thank you. Thank you all, and thank you, Joseph, for making this happen.